Hello, everybody, and welcome to this first lecture on competition mathematics. We're going to start with some basics of number theory. Now, this is my first time using OBS, so apologies. I may need some understanding today while I'm figuring out how to use all this stuff. Okay, so let's get started. First thing we're going to do is we're going to look at some of the number sets that that we use. The most obvious one is the natural numbers. That is the set of counting numbers. 1, 2, 3, and so on. Now, we'll come across the natural numbers quite often. We'll also come across a special variation of the natural numbers, which is the natural numbers including 0, which we'll call non-negative integers, which brings us to the integers, which we indicate by z. And that's the set minus 3, all the negative whole numbers, and so on, the positive whole numbers. And then the other number set that we will come across quite often, the rational numbers. And I'm going to just define those as the set of numbers a over b, where a and b are in the integers. B is not equal to 0. And if we want, we can specify, but it's unnecessary, that the least common denominator between the greatest common divisor between a and b is 1. So which we indicate the notation we use for a greatest common divisor. There are two shorthands that are used in competition math. There's that, and the other one is just a b is equal to 1. If you have parenthesis a b equals 1, that means that the greatest common divisor of a and b is 1. Another way that you will see that written is to say that a and b are relatively prime. That is, that they are prime relative to each other. So let's talk about some interesting subsets of the natural numbers. Well, I just mentioned one. P is prime in the natural numbers if it's divisible only by if it's only look at that. It's only factors in the natural numbers are itself and 1. So that's one we'll see quite often. I'm not going to go into the additional details about the even numbers, the odd numbers. Even numbers are numbers which are divisible by 2. And of course, we build a lot of things based on these. And let me introduce you to one of the fundamental theorems of arithmetic. In fact, it is called the fundamental theorem of arithmetic, because it's so important. The fundamental theorem of arithmetic says that every natural number n has a unique, this is a very important word, factorization prime numbers. And we write that factorization. For some reason, we use alpha for exponents in number theory quite a lot. So we write n as the product of p1 to the alpha 1, p2 to the alpha 2, and then pk to the alpha k for some k with the set of p's are prime numbers. And the set of alphas are natural numbers. And we can already use this fundamental theorem. It seems reasonable, right? It seems like this is obvious, but we can already use this fundamental theorem to prove some nice results. For example, let's prove that the square root of 5 is irrational. Well, the way we prove that is we prove it using a technique called proof by contradiction. We assume that square root of 5 is rational, and then we show that that results in some absurdity. So what does it mean to be rational? It's equal to a over b with a, b in the natural numbers. Well, or in, I should say, in the integers. But since the square root of 5 is greater than 0, we would be okay if we said in the natural numbers. And the greatest common divisor between a and b equal to 1. So if we can find any rational number written as a over b, we can find its greatest common divisor, divide a by that, divide b by that, and we get eventually to the simplest form of a fraction, right? That's pretty obvious. So what does that mean? Well, that means that if we square both sides, we get 5 is equal to a squared over b squared, which implies 5b squared is equal to a squared. But now we go back to our fundamental theorem of arithmetic, right? The left-hand side divisible by 5. So the right-hand side must be divisible by 5. So we use this notation. 5 divides a squared. Now, but since a is an integer, if a squared, 5 divides a squared, then 5 clearly must divide a. So we can write a as 5 times n for some n in the natural numbers. Sorry, in the integers. So what happens when we put that back in here? Well, we get 5b squared is equal to 25 n squared. When we square out a equals to 5n, we get 25n squared. So we get b squared is equal to 5n squared. And we're back to where we started, right? 5 must divide b. But if 5 divides b and 5 divides a, that means that the greatest common divisor of a and b must be a multiple of 5 for some integer. And it's not equal to 1, and that is our contradiction. So the only assumption that we made was that we are not sure if it was true or not is this one, that the square root of 5 is equal to a over b. So we've just shown that square root of 5 is irrational. And that completes the proof. Now we can also use this fundamental theorem to find some interesting characteristics of numbers. For example, how many positive integer factors does 36 have? Well, writing 36 as a product of primes, we've got 36 is 2 times 18, and that's 2 times 9, that's 3 times 3. And that's our unique factorization, 2 squared times 3 squared. Now, how many factors does that have? Well, we know that every factor of 36 must have the same form. Two to the alpha times 3 to the beta, where alpha is one of 0, 1, or 2. Because if it has more than 2 2's, if it's divisible by 2 to the 3, then it won't divide into 36 because 8 does not divide into 36. And similarly for beta, that must be one of 0, 1, or 2. And so we can now write out all of the factors of 36 by writing alpha on one axis, 0, 1, 2, and beta on the other axis, 0, 1, 2, and finding out and we can't have anything else because there's no other primes in the prime factorization of 36. So when we've got alpha 0 and beta 0, that gives us 1, 2 to the 0 times 3 to the 0. This is 3, this is 9, 2, 6, 18, and finally 4, 12, and 36. And we have all of the factors of alpha of 36 in this grid. So we end up with 3 choices for alpha and 3 choices for beta. So we've got 9 factors. Okay, so we're going to look at one more type of question. I'm going to give you two questions to work out on your own. First is how many factors does 720 have? And the second, how many zeros are there at the end of 20 factorial? Now I'm going to explain what a 20 factorial is. 20 factorial is what you get by multiplying 20 times 19 times 18 times 17 times all the way down to 2 times 1. We'll come across factorial in another lecture on combinatorics and how many ways you can arrange and choose things from different groups. But for now, I want you to just think about the prime factorization of 20 factorial and how you figure out how many zeros there are at the end. Okay, so let's look at question 1. How many factors does 720 have? Well, 720 is equal to 2 cubed times 3 squared times 5. Actually, do you know what? It's 2 to the power of 4. It's 36 times 10 times 2. So every factor are of the form 2 to the alpha times 3 to the beta times 5 to the gamma. Just picking random letters with alpha coming from 0, 1, 2, 3, or 4. Beta can be 0, 1, or 2. And gamma can be 0 or 1. Total number of factors, 5 choices for alpha, 3 choices for beta, and 2 choices for gamma. So we get 30 factors. Okay, question 2. How many trailing zeros in 20 factorial? Well, what do you need to have a trailing zero? You need to have a factor of 10, right? We've got it's going to be something by 10 to the k, right? And the number of tens is the number of trailing zeros when we get to something where n is not divisible by 10. Well, what do we need to get a 10? That's going to be equal to n times 5 to the k times 2 to the k. So let's see if we can find out how many 5s are in 20 factorial and how many 2s. Well, for the 5s, it's pretty easy. We've got 1 5 from the 5. We've got 1 5 from the 10, 1 5 from the 20, and 1 5 from the 15 in the product. So we've got 4 5s, right? 20 gives you 1 5. 15 gives you another one. The 10 gives you another one. And then finally, we've got the 5 at the end. So we've got 1, 2, 3, 4 5s. Okay, for 2, it's a little bit trickier. In fact, we could just say, well, every even number is divisible by 2, so that's going to be at least 10 even numbers are going to be divisible by 2. And we could stop here. We could say, well, we've got at least 10 2s. We've only got 4 5s, so we know we're going to have enough 2s to cover all of the 5s to make 10s. But let's keep going, right? Well, we're going to get 1 2 from 2. We're going to get another 2 from the factor 4. We're going to get another 1 from the factor of 6. So that gives us 4 2s so far up to 6. And then from 8, we're going to get 3. And so on. So let's see if we can figure out a logical and sequential way to figure out how many 2s there are in 20 factorial. Well, let's take 1 2 from every odd even number. Okay, so that's our 10. And now we've got how many multiples of 4 between 1 and 20? Well, we've got 4, 8, 12, 16, and 20. We've got another 5. And each of those are going to have at least 2 2s in their prime factorization. But then we also have the multiples of 8, right? We've got 8 and 16. So that's another 2. And then we've got 16, which is 2 to the power of 4. So that gives us another 1. So in total, we're going to have 10 plus 5 plus 2 plus 1 factors of 2 in our prime factorization, gives us 18. And you can figure that out on your own. If we take, for example, 8 factorial, that's equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, we've got 3 2s here. We've got 1 here. We've got 2 here. We've got 1 here. Gives us 7. And that's the same as 8 divided by 2 plus 8 divided by 4 plus 8 divided by 8. And that's not a coincidence. But we'll come back to that in another episode, right? So what we know is we've got 18 2s and 4 5s. So we know we've got 4 zeros at the end. Of 20 factorial. Ta-da! Okay, so let's stop there for the time being. I will send you a problem sheet which will have a number of other problems in it. And in the next episode, I think we're going to look at some other number theory problems, the perfect numbers and Pythagorean triples, and see if we can learn some interesting things about those. Thank you very much.